We're going to continue with the respiratory system. And in this mini lecture, we're going to consider the mechanics that draw air into the lungs. So our focus continues on the lungs and the exchange between the gases that are inspired and the blood that flows through the lungs. And our question is quite simple. How are the lungs ventilated? That is, what is it about our musculoskeletal system and the anatomy of the respiratory system that facilitates exchange? We've already established some of the basic principles about the exchange that occurs, but now we're going to consider at a larger scale how that exchange is facilitated by ventilation. So we're going to start with anatomy. Now, inside of your rib cage, there's a space, and that space is filled with your heart and your lungs. That space is known as your thoracic cavity. So the respiratory system resides largely within the thoracic cavity. Because I guess you could consider this stuff up here as being outside of the thoracic cavity. But of course you inspire air through your nose and through your mouth. It travels through the trachea and then enters into the lung. Now, on the floor of the thoracic cavity is a really important muscle for the respiratory system. It's known as the diaphragm. And we're going to consider what that does in a moment. If we were to dissect the lungs, then we would find its very elaborate branching network of vessels. The air comes in on a large bolus, but the goal of this anatomy is to essentially partition that large volume of air into very small packages so that diffusion can allow for the gases to exchange with the blood. So here we see a schematic that's more explicit about that anatomy. So we have the right and left lungs here. And you can see there's a whole elaborate network of branches. And here we see one of those branches where we've pruned off the smaller vessels. So air would be flowing into this larger vessel until eventually it gets down to this group that look like bunches of grapes. And if we focus in on one of those bunches of grapes, here's a cutaway where the air would flow. And then surrounding each of these grapes are capillaries. And you can see that they branch, and that allows for exchange to occur with the gases in the interior. So these grapes are known as alveoli. The singular is alveolus. And the alveoli are the site of exchange. Now, driving the airflow into the lungs are a set of muscles. And there's one category of muscles that's activated on inspiration, that is the action that drives air into the lungs, and then another set that drives expiration. So for inspiration, that diaphragm muscle is really important. So we have the diaphragm here, and we'll consider how it changes shape in order to drive inspiration. And then there are muscles associated with the ribs. Those are called the external intercostals. And we can see that they surround the rib cage. And when those muscles contract, they serve to expand the thoracic cavity by expanding the volume contained within the rib cage. Okay, so the rib cage wraps around the thoracic cavity, and anything that serves to expand its volume, or the volume contained inside of the ribs, are going to expand the volume of the thoracic cavity. And inspiration is driven by an expansion in the volume of the thoracic cavity. So we've talked about Boyle's law in an earlier lecture, and that illustrates that when you have an increase in volume, you'll have a momentary drop in pressure. And that's what draws the air into the lungs on inspiration. Now, another set of muscles that matters here serve to rotate the rib cage forward, which also allows for an expansion of its volume. And these muscles are known as the scalene muscles. So what we see here is the most anterior portion of the rib cage. So here's the sternum. Here's the spinal column. And what we have here are muscles that show their insertion onto the rib cage. Those are the scalenes. So when they contract, they rotate the rib cage forward, which also serves to enhance the volume of the thoracic cavity. Now, when you exhale, or you undergo expiration, then the goal is to reduce the volume of the thoracic cavity, which was just inflated on inspiration. And that's achieved by muscles between the ribs. Okay, it's subtle, but these muscles are below those external intercostals we saw a moment ago. And when these muscles contract, they're called the internal intercostals, then they reduce the space between the ribs. And that serves to reduce the volume contained within the rib cage, that is, the volume of the thoracic cavity. Also, the abdominal muscles, okay, so the six-pack muscles, which would be right here on the body, they're not shown. Those abdominal muscles are used on large expiration, so they essentially reduce the space within your viscera, and that serves to reduce the volume as well of the thoracic cavity. So again, we can see that they are all over the rib cage, and when they contract, they reduce the volume inside the thoracic cavity. All right, so let's look a little more carefully at what the diaphragm muscle does. The diaphragm muscle has a concave shape at rest. This is the resting form of the diaphragm muscle. And when you look at the diaphragm muscle in 3 dimensions, it's actually really complicated geometry. But as far as we're concerned, all that really matters here is that when it's relaxed, it has a concave shape. And that shape pushes on the floor of the thoracic cavity and serves to keep the volume of that cavity relatively small. So when you relax, when you expire the air in your lungs, there's a compression on the lungs that serves to reduce the volume of the thoracic cavity, which momentarily elevates the air pressure and thereby drives air out of the lungs and is exhaled into the surrounding air. All right, so the diaphragm relaxes for that to happen. When the diaphragm is instead contracted, then we have the reverse. There's essentially a dropping in the floor of the thoracic cavity. So this muscle is kind of funny because, when it's contracted, it takes this shape. It's a more flattened shape, and you can see that it's lower, more posterior on the body than when it's relaxed, like here. So that muscle, the diaphragm, contracts when we have a contraction of the scalene muscles and the external intercostals, which serve to expand the thoracic cavity. That increase in volume drops the air pressure inside of the lungs, and air, just like blood, will move to wherever there's lower pressure. So if the air inside of the alveoli, inside of the lungs, is low, that's going to draw air into the mouth, and it will fill up those spaces inside of the lungs. Whereas if we have a compression or a decrease in volume, that elevates the pressure, which drives air to where the pressure is relatively low, that is outside of the body. So these changes in volume and pressure can be modeled using a physical analogy. So we have a respiratory mechanical model where we have essentially a beaker that's serving as our thoracic cavity in this model that can change in its internal volume with the plunger shown there in gray. The plunger simulates what the muscles around the thoracic cavity achieve. And we'll focus on the diaphragm muscle, but really the physical model on the left is showing volumetric changes that are achieved by the diaphragm, also by the internal, external intercostal muscles and the scalene muscles as well, and for that matter, the abdominals. So they all serve to change the volume of the thoracic cavity. Now, the lungs are not a closed volume as we see on the left, but instead they're open to the outside. And so we're going to modify our physical model by putting a little hose on it, and that allows for gas to exchange with the surroundings. So when we decrease the volume, we're elevating the pressure inside of that space, and those gas molecules will then move to where the pressure is less outside of the body. Now, another feature of the anatomy that turns out to matter to its functioning is a cavity that is wrapped on the interior of the thoracic cavity. This is known as the pleural cavity, shown in the dark red. The pleural cavity is a closed, liquid-filled interface between the thoracic cavity and the lungs. It's lined on the interior of the rib cage, and the lung tissue is very delicate. It has those very fragile alveoli and a lot of connective tissue, and when your rib cage moves to facilitate breathing, there's some amount of shearing between that delicate tissue and the interior of the rib cage. The pleural cavity, in part, reduces the potential damage to the lung tissue because it's liquid filled with essentially a lubricant that allows for the surface that is adhered to the lungs to slide relative to the surface that is attached to the interior of the rib cage. Another feature of this is that the pleural cavity helps the alveoli stay inflated at rest. When the pleural cavity is punctured, like if somebody is unfortunately stabbed through their ribs, and that causes a puncturing of the pleural cavity, then there is a catastrophic drop in a negative pressure in the pleural cavity that helps to keep the alveoli inflated, and that results in what's called a collapsed lung. So a collapsed lung is a decrease in the volume of the alveoli and essentially a shriveling up of the lung, which greatly compromises its ability to fill up with air. So we're going to consider the pleural cavity and its changes in pressure relative to the pressure changes that we see in the alveoli. And we're going to do that by thinking about those changes with respect to our mechanical model on the left. And what I've done is to redraw it here so we don't have the individual gas molecules illustrated, but instead the gases are shown in this light blue color. And we're going to track a series of physiological parameters. First, we have the lung volume. This would be the total volume taken up in the lungs as a function of time. And of course, on inspiration, as the thoracic cavity increases its volume, then we have a drop in pressure and a filling up of the lungs, like that. And note, this is a change in volume. We'll get into the fact that the lungs before inspiration, like in this kind of state, have a volume. And that volume matters to how it functions. But this is a change, and so we're starting at 0 here. And so this would be the amount of air that is inspired. Let's look at pressures. So here we have the pressure of the pleural cavity. Now, I mentioned that the pleural cavity has a negative pressure. Okay, that's negative relative to atmospheric pressure, negative relative to the air pressure that's inside of the alveoli. And note something here. It goes from a slight negative value to a bigger negative value on over the course of inspiration. Whereas when you look at the pressure in the alveoli themselves, you get a very different relationship. So a lot of people find this to be rather non-intuitive. Why is it that the alveoli drop in pressure but then go to 0? Let's think about that. this is an open system. Boyle's law doesn't really apply in this case because the number of molecules, of gas molecules, is not fixed. Instead, what's going on here is that as the thoracic cavity expands in its volume, there's a momentary drop in pressure. But because the system is open, that drop in pressure is compensated for by the gas molecules that move into the lungs from the outside. So this drives airflow that is then filled up by the increase in the lung volume. In contrast, the pleural cavity is a fixed liquid volume. So this, even though there's sort of a little notch in here, you can imagine that the pleural cavity is a membrane with a hole in the middle of it, but that hole does not mean that liquid leaks out of it. It's instead sealed around that opening so that the air can flow into the lungs through the pleural cavity. But the pleural cavity itself is a fixed liquid volume. So if it's a fixed system that has a constant volume, or a constant volume of liquid, then as you pull on it, just imagine putting your finger on the end of a syringe, and when you pull in the plunger, because you have now capped off the volume inside of the chamber, now when you pull on the piston, you can feel the low pressure pulling on your fingertip into the interior of the piston. The pleural cavity is kind of like that. As the thoracic cavity expands in its volume, the volume of liquid in the pleural cavity doesn't change, and instead that thoracic cavity is pulling on the pleural cavity and serving to drop its pressure, which is great because the pleural cavity again helps keep the lungs inflated, and the interior membrane of the pleural cavity pulls out on the lung tissue to maintain that large lung volume. On expiration, we have a reversal. So the thoracic cavity reduces in its volume. There's that drop in volume that we see there. The alveoli now have a positive pressure, okay? Right here at the end of inspiration, you have all those moles of gas entering into the alveoli, and they've reached equilibrium with the outside world. So if you're at atmospheric pressure, say a sea level, an atmosphere of 1, then at the end of inspiration, you've achieved the same pressure inside of the lungs as outside. So that's a 0 pressure. As soon as you start to compress the thoracic cavity, now you're reducing the volume of space occupied by those gas molecules. So we're here on the curve. And according to Boyle's law, at least momentarily, we'll have an increase in pressure. It's an open system, which violates Boyle's law. So we have the elevation in pressure, but then it goes back to 0 at the end of expiration. As there's less of a volume change, now there's less of a driving force, and we're losing those gas molecules to the outside world. The pleural cavity does increase as the volume goes back to its starting point on this graph, but it remains at a negative value because the pleural cavity always maintains a negative pressure. That's why we had the collapsed lung phenomenon. If the pleural cavity membrane is ruptured, then that negative pressure is no longer maintained, and that ceases to allow the lungs to stay inflated. So this is what's known as the respiratory cycle. Let's consider the volumes of the air that's inspired relative to what's there at rest. So this would be, I'm going to show you the volumes that are involved here for shallow breathing. One interesting aspect of the respiratory system is how flexible it is. You can inspire a broad range of volumes, and we'll get to that in a moment, like if you exercise. Now, not all air that you inspire makes it to the alveoli and therefore has the opportunity for exchange. There's the lung trachea. There are all of the many vessels that don't include the alveoli, and exchange only happens at the alveoli. So if you were to add up the total volume of all of the air that you inspire that doesn't make it to the alveoli, that's about 150 milliliters. And that volume is known as the dead space. Okay, so we're at a point in the respiratory cycle where we're about to take a breath. And there has been sufficient time for the air inspired from the previous breath to reach equilibrium with the blood. And so we would say that the air is deoxygenated because it has the same partial pressure as the blood. Now, note something here, that there's a volume. Okay, we're about to do inspiration. There's a volume here at rest within all the alveoli and the dead space. Actually, so schematically, this tube up here represents all the dead space. So that's not just the trachea, but all of the air passages where there aren't alveoli. Or I should say air passages, because alveoli aren't air passages. So all the air passages, including the trachea, is represented here. This volume down here is meant to represent the alveoli. This is all the exchange that occurs. Now, if we add up the dead space to all that space there, it is a pretty big number compared to the dead space that we can compare it to. All right, so 2350 milliliters is a pretty large volume. Now, you might sort of tend to think like, well, I exhaled and therefore all the air left, but there's this large volume that remains in your lungs. All right, so let's look at other states in the respiratory cycle. So we have at the end of inspiration, so the goal with inspiration is to bring oxygenated air in, right? So that's what we see here. So on the end of inspiration, we have that volume of air brought in. So for shallow breathing, this is when you're at rest, the total inspired volume is 500 milliliters. The amount that reaches the alveoli, the amount that can be exchanged with the blood, is 350. Where does that come from? Well, we take the total inspired volume and we subtract from that the dead space, all the air passages. That leaves us with 350. 350, okay, so 500, the inspired volume, you can see is small compared to what was left behind at the end of the last breath. All right, so that puts it a bit into context. There's actually a pretty big volume inside of your lungs, even at the end of a breath. Now, we allow for exchange to occur, and we're going to exhale. So in the end of expiration, we breathe out an equal amount of air as we inspired in. Now let's look at the color coding here. Every time you exhale, you breathe out 150 milliliters of purely oxygenated air. All right, it's pretty inefficient because why is there 150? Well, it's equal to the dead space. Since the air didn't exchange with in the alveoli with the blood, then we just end up exhaling exactly the same quantity, and we failed to take advantage of that oxygenated air. We have 350 deoxygenated milliliters because that's the volume that exchanged with the alveoli down here. And then in the alveoli, we're left with 2200 milliliters. Okay, so this functional residual capacity is the volume of the alveoli plus the dead space. That volume of air that you exhale is known as the tidal volume. It's also the amount that we inhale, 500 milliliters. So now, if we were to study the respiratory system and to consider its performance, then we'd be interested in how much exchange occurs. So in the case of the cardiovascular system, we had this quantity, the stroke volume, which was the heart rate. I'm sorry, we had the cardiac output, which was equal to the stroke volume times the heart rate. Here, the respiratory system has something analogous, which is the pulmonary ventilation. It's the ventilation rate times the tidal volume. Okay, so look at the units. Milliliters per minute is our measure of ventilation. That's how frequently you breathe times how much you inspire. And you can measure that quite simply with a spirometer. And from a spirometer, you can infer the changes in lung volume. Well, you can measure the changes in lung volume, but if you know the functional residual capacity, then you can infer from the air that emerges from your mouth how much is turned over inside of the lungs. So let's just consider the kind of shallow breathing that we just talked about, where we have oscillations between 27 and 2200 milliliters with that 500 milliliter tidal volume. And here we see that plasticity in the respiratory system. You have the ability, because skeletal muscles are driving these changes in thoracic volume, you have the ability to actively, consciously change the volume of the thoracic cavity and therefore the volume inside of the alveoli. So if you take a deep breath, you can draw in a tremendous volume of air compared to the shallow breathing. And if you pull in as much air as you're physically capable of, that's known as the total capacity. And a lot of very successful aerobic athletes have a greater total capacity than the rest of us. And it can be improved a bit by training, but it's also a function of what you're born with. It's a sort of an anatomical feature of the lungs. And as I've mentioned, aerobic performance is limited by your respiratory system. So this gives aerobic athletes an advantage. And then you can also drive a lot of air from the lungs. So you can create a lot of turnover of the gas mixture inside of the lungs. So you have the deep expiration shown there. And then we go back to shallow breathing. Now, this all has to do with ventilation. But of course, we're ventilating the lungs so that we can allow for gas exchange to occur. And there's, it turns out, a nonlinear relationship between ventilation and the partial pressures that are achieved within the lungs. So we just saw in the previous slide how the oxygenated air that comes in is actually a small proportion of the total air that's inside of the lungs. And as you ventilate more, then you're going to increase that mixture, but that increase occurs in a nonlinear fashion. So let's take a look at that. Now, first, I want you to just take a look at this quantity up here. It's momentarily going to disappear, but we have the pulmonary ventilation as the ventilation rate times the tidal volume. So the tidal volume is the total inspired air, but it doesn't take into account the dead space. So if we really want to know what exchange is occurring, then we'd want to subtract the dead space from the tidal volume. And that's what's known as the alveolar ventilation. So here we have the ventilation rate again, and the tidal volume, but we've subtracted the dead space. So this is telling us how much ventilation is occurring at the exchange surfaces. And that's what we have on the x-axis here, which is how much ventilation occurs in the alveoli. And then here we see on the y-axis the partial pressures that is achieved. If we can assume that the circulatory system does its part to allow the blood to achieve equilibrium with the air, then we can infer that the alveolar partial pressure would be equivalent to the partial pressure achieved within the blood. Now at shallow breathing, we have a higher partial pressure for O2 as CO2, right? And we know from Dalton's law that that makes sense because there's a higher proportion of the air that we inspire that's going to be oxygen molecules. There's 21% is oxygen molecules. But that very high proportion of oxygen molecules are now on inspiration going to mix with the relatively deoxygenated air inside of the lungs. So even though there's greater oxygen in the air by orders of magnitude, for the gas mixture inside of your lungs, it's not quite as favorable because we have that 21% then diluted into the deoxygenated air. So we're only seeing a difference of 100 millimeters of mercury for a PO2 compared to 40 for the partial pressure for CO2. Now, if you force yourself to breathe at a really high rate, and sometimes this can be triggered by panic attacks, or sometimes you just want to cause yourself to pass out, I guess, then you can move right on this curve. Now, hyperventilation is also partially a function of your own metabolic rate. Okay, hyper implies more than what is necessary or more than what is normal. And that, in this context, refers to what is needed for your own metabolism. So hyperventilation would be a greater respiratory rate than what is necessary for your own metabolic needs. And you can drive yourself to do this, even though it will cause lightheadedness and may eventually cause you to faint. And the reason why you faint, just as an aside, is that this hyperventilation drives a drop in the partial pressure for CO2. That increases blood pH. And an increase in blood pH causes a constriction of arterioles in your brain, and which in turn causes you to pass out. So it effectively is a mechanism that stops you from hyperventilating any further. I'm not sure if this is by design or sort of an accident, but you can think of it as a sort of physiological mechanism to stop you from being stupid and hyperventilating. Now, on the other side of the curve is a more dangerous situation. If you're ventilating less than your metabolism requires, then what you find is a precipitous drop in the partial pressure for oxygen and a large rise in the partial pressure for CO2. Now remember the values here. The blood that returns to the lungs has a partial pressure for CO2 of 46 millimeters of mercury and about 40 millimeters of mercury for O2. So, with a less than half drop in the ventilation rate, we can see that effectively the lungs are doing virtually nothing because the partial pressure for O2 that's arriving at the lungs is already at a level that's comparable to what can be achieved by the ventilation rate of 2 liters per minute. So it doesn't take much of a drop in your ventilation to have a catastrophic effect on the dissolved gases in your blood, effectively making the lungs non-functional. Now, as a reminder, the alveolar rate is not equal to the pulmonary ventilation because the pulmonary ventilation doesn't take into account the dead space. All right, so hyperventilation will cause lightheadedness because of its influence on blood pH, and that can cause you to pass out. Whereas hypoventilation, insufficient ventilation, causes a very large drop in blood pH. Your blood becomes very acidic when your partial pressures for CO2 become that high. But perhaps more alarmingly, we have this dangerous hypoxia or insufficient oxygen for aerobic metabolism. Okay, so how are the lungs ventilated? We've considered 3 major factors here. First of all, we have the muscles for inspiration and expiration. We've itemized those, driving pressure changes in the lungs that draw air in and expire air when you relax the diaphragm and the external interscalines, for example, or external intercostals and the scaling muscles. Second, the volume of air exchange is a portion of inspired air because of the dead space, and that amount of oxygenated air is small compared with the functional reserve capacity, that is the volume of air inside of your lungs after expiration. And then finally, we just saw how hypoventilation has catastrophic effects on gas exchange.